Hey there, and welcome to The Explainer. Today, we're going to demystify exactly how machines learn to outsmart us, and we're doing it by diving into the foundational concepts of reinforcement learning. It's this absolutely fascinating topic that bridges the gap between pure biological instinct and cutting-edge AI. I am so thrilled to unpack this with you all, so let's get right to it. Okay, so picture this. A gazelle calf struggles to its feet in the savannah, and literally minutes later, it's sprinting at 20 miles per hour. I mean, how does it learn this without an explicit teacher? Or, think about how a human infant figures out how to wave its arms. It all comes down to pure natural trial and error. Just actively interacting with the environment produces this massive wealth of information about cause and effect. Today, we're going to look at how we take that exact, brilliant biological concept and translate it into a computational approach. And here's our roadmap for the explainer. We'll start with what reinforcement learning actually is, break down its 4 key elements, watch how machines play games, tackle that classic explore versus exploit dilemma, and finally, wrap up with the history of the field. Let's jump in.
All right, section 1, what is reinforcement learning? Let's establish our baseline. This right here brilliantly illustrates the whole shebang. You see, in most machine learning, specifically supervised learning, an external teacher provides correctly labeled training data. They're essentially spoon-feeding the machine, right? But reinforcement learning? Totally different beast. It is a closed-loop system. It learns via evaluative feedback and trial and error just to maximize a numerical reward. No one is telling the learner what to do. It just has to go out there and actively discover which actions yield the absolute biggest payoff. Which brings us to section 2, the 4 key elements. Let's break down the core components that actually make an intelligent agent tick. First up, we've got the policy. Think of the policy as the agent's brain. It's essentially a map from the perceived states of the environment to the actions that need to be taken. It directly dictates what the learning agent is going to do at any given second. If we're talking biology, this would be like your natural reflexes or a deeply ingrained habit.
Next is the reward signal. And this is a single number sent by the environment at every single time step, defining the immediate goal. You can really think of this as being the machine equivalent of pleasure or pain. The reward signal bluntly tells the agent, hey, what you just did is immediately good or bad. So the absolutely crucial point here is that altering the policy to maximize this total signal over the long run, that's the agent's one and only objective.
But honestly, the real magic happens with the value function. While the reward signal is all about immediate pleasure or pain, the value function predicts what is good in the long run. We're seeking actions that bring about states of the highest value, because those guarantee the absolute greatest reward over time. It requires the agent to be incredibly farsighted, which, as you can imagine, is vastly harder than just chasing an immediate short-term high. And finally, we have the model of the environment. Now, this is an optional element, but it mimics how the environment behaves, allowing the agent to make inferences and actually plan before it acts. The model gives the agent foresight. It essentially bridges that huge gap between simple low-level trial and error learning and high-level deliberate planning. Bringing it all together, we can see exactly how these pieces interact. The agent perceives the environment's state, its policy dictates an action, the environment fires back a reward signal, the value function steps in to update those long-term estimates, and if it's there, the model allows for future planning. It creates this beautifully dynamic, continuous cycle where the agent senses, acts, and just constantly refines its understanding to achieve its goals. Let's move on to section 3, how machines play games. We're going to see how these 4 elements actually build a master player using a classic game of tic-tac-toe. Now check this out. Imagine the machine essentially thinking ahead. It starts by mapping out a table of numbers, literally one for every single possible board state, representing its estimated probability of winning from that position. That right there is our value function in action, constantly evaluating the best path forward by scanning all potential futures. Most of the time, the machine is going to act greedily, right? It just selects the move with the highest estimated chance of winning. But notice that little exploratory move labeled E. Every now and then, the machine purposely chooses a random path instead of the obvious one. Why? Well, it gets to experience totally unique scenarios it might otherwise completely miss, and that is absolutely vital for discovering new, totally dominant strategies. So how does it actually update its brain while doing this? Well, during play, it uses something called temporal difference learning. The machine tracks the outcomes and literally backs up the value of a later state to adjust the value of an earlier one. By moving the earlier state's value just a tiny fraction of the way toward the newly discovered future value, it is actively rewiring its own expectations on the fly. As the agent looks at multiple paths, it just keeps tweaking. And let me tell you, over thousands of games, these tiny fractional adjustments make the machine's estimates completely lethal. It actually learns to set up multi-move traps for short-sighted opponents. It practically steers the opponent into losing based on these deeply refined estimations. And that is the true power of this method. This sort of flipbook-like process of evaluation yields an absolute master player. And it does it without needing a complete upfront model of the opponent and without having to exhaustively search every single possible move. It literally just learns by doing.
Okay, that brings us to Section 4, Explore versus Exploit. This is a massive philosophical tension driving all of machine learning.
It really boils down to this. Do you stick with a winning move or risk it all to find a better one? I mean, seriously, ask yourself. When you're navigating uncharted territory in your own life, do you exploit what you already know works for a guaranteed reward? Or do you explore to maybe find something entirely new? In reinforcement learning, this dilemma is famously known as the N-armed bandit problem. Picture a slot machine, a one-armed bandit. But instead, you've got N different levers to pull, and every single one has a different, totally unknown payout rate. You have to repeatedly choose among these levers to maximize your total expected reward. It hits the nail on the head regarding that conflict between exploration and exploitation. Actually, a great real-world analogy is a doctor choosing between experimental treatments for a series of sick patients. They have to balance using the best-known treatment with the urgent need to discover even better ones to maximize survival rates over time. When we compare the math on strategies, it gets really fascinating. A purely greedy strategy always maximizes short-term gain based on what it currently knows, but it usually totally misses better unknown actions. An epsilon greedy strategy, on the other hand, it acts greedily most of the time, but it retains a tiny, tiny probability, called epsilon, of just picking a random action. And over the long run, that tiny bit of exploration guarantees the machine won't get stuck in a rut. Let's head into our final segment, Section 5. The history of RL. Let's look at how all these ideas finally merged. The history of reinforcement learning isn't just one boring, straight line. It's a brilliant collision of entirely different disciplines. Way back in 1911, Thorndike established the law of effect in animal psychology. Then, by 1948, the legendary Alan Turing was already proposing computational pleasure-pain systems. In the 50s, Richard Bellman hammered out the math for optimal control. But it wasn't until 1989 that Chris Watkins developed Q-learning, finally unifying animal psychology, early computing, and control theory into the modern AI framework we know today. Pretty amazing stuff. As we wrap up this explainer, I want to leave you with a thought. How does this simple trial-and-error algorithm, this delicate balance of cashing in on familiar rewards versus the risk of pure exploration, mirror your own daily decision-making? I'll let you ponder just how closely these cold mathematical frameworks actually reflect the way you navigate your own life. Thanks so much for joining me on this deep dive. Keep exploring, and I'll catch you next time.